Today will be a continuation of the previous two lectures from climatology. So in the previous two classes, we saw thermal comfort, thermal quantities, principles of thermal design. And today we'll be looking at solar architecture and natural ventilation. So whatever we learned previously had everything to do with heat and that part of climatology, right? So today's lecture has nothing to do with heat. It has everything to do with the sun and the wind. We're going to look at sun path diagrams, sun shading devices, and how to calculate these sun shading devices, and natural ventilation. What are the driving forces behind natural ventilation and how to calculate these? So let's move on to the first slide. Okay, so in solar architecture, there's the first slide. It becomes important to know how the earth and the sun revolve each other and what exactly is the relationship between the two. Okay, so as we know, the sun is the earth revolves around the sun, and the earth is not really a spherical shape. It's called a geoid. Okay, so it's not exactly spherical, and it obviously has an equator and an angle at which it rotates. This axis is the axis around which the entire mass of earth rotates. But this angle is not exactly 90 degrees, right? It rotates at a tilt. So the equator and the central line, etc., the angle at which it rotates, this axis. Does anyone know what the angle is? The angle of rotation of the earth or the earth's axis. (180). Another guess? Any other guess? The angle is always measured with respect to the perpendicular, right? So let me just use another color. So if this is the perpendicular and this is my angle of rotation, this is the axis. 23.5 degrees is the axis, right? So the earth rotates at an angle of 23.5 degrees away from that perpendicular, right? So again, this angle is 23.5 degrees. Yes. So because of this, what happens is that as the earth rotates and revolves around the sun, this axis causes the earth in 4 extreme positions, right? To be in 4 extreme positions. So seasons essentially are caused because of this tilt. So as the earth is in this position, this portion of the earth is exposed to sun, which means that everything in the southern equator, which is what is exposed most to the radiation, is having the summer seasons, right? And the northern hemisphere is having winter. Similarly, the other opposite end is when most of the northern hemisphere is here exposed to the sunlight, and all the regions away from the sun here experience winter. Winter in the southern hemisphere during June, and summer in the northern hemisphere. Similarly, the opposite end, in December, the north will have winter, and the southern hemisphere will have summer. The seasons are reversed. Whereas in March, an equinox or spring is what we call it, is again, similarly, it's opposite for, it's equal on either end. That's what an equinox is. So the days and the duration of the day versus night is similar on both the ends because an equal amount of the Earth's surface is exposed to the sun. Does anyone know the dates for the winter and summer solstice for the northern hemisphere? Solstice is when we have the extremes. These conditions are known as solstices. So in the northern hemisphere, which is where we are. India is in the northern hemisphere. Does anyone know the date for summer solstice? This is the longest day in summer, or the longest day, which means we'll have daylight for the maximum amount of duration or the maximum amount of hours. This happens on June 21st. Okay. But this same date in the southern hemisphere will be the winter solstice, because they're having winter at that time. Winter solstice again is the day with the least amount of sunlight or the least duration of sunlight. Right? Summer solstice in the northern hemisphere and winter solstice in the southern hemisphere happens on June 21st. Similarly, winter solstice in the northern hemisphere which is the shortest day, happens on December 21st. For the southern hemisphere, it will be the summer solstice. So the southern hemisphere, this is the northern hemisphere. Okay. So the longest day in the southern hemisphere will be on December 21st, which is their summer solstice. So as far as India is concerned, summer solstice is on June 21st, winter solstice is on December 21st. The summer and autumn and spring equinoxes, which is March, will be your spring equinox. Which means that the amount of day and night is almost equal. The duration of day and night is almost 12 hours each. So that happens on March 21st. Some books say it's the 22nd of each month, but the widely accepted date is 21st, March 21st for spring equinox. And at the same time, the southern hemisphere will have their autumn equinox. Okay. And the reverse is for September 21st or the September equinox. Remember these dates, the 21st is common for all of the months. June will be summer in the north, December is winter in the north, spring is March, and autumn is in September. So in the southern hemisphere, September 21st will be the spring equinox. Okay. So all of these different seasons and this variation in the north and the south hemispheres happens only because of the tilt of the Earth's axis. It's not perpendicular to its axis of rotation, and because there's a tilt and it rotates around that axis, there is only a certain part of it exposed to the sun at certain durations or certain period of months, right? 3 months each or 3 to 4 months each. That is why it causes seasons. Okay. Any doubts here? Shall I move on to the next slide? This is all, I think, 6th or 7th standard social studies we've learned it. It's just a brush up, and we'll see how this is represented on a sun path diagram, which we all use. Any doubts here? No. All right. I'll move on to the next slide. You all can just type in the chat. I'll always keep an eye on it if you're not comfortable speaking, or you can always use the mic, unmute yourself and speak. All right, so sun path diagram, something we all love to put in our site analysis and concept sheets. Let's see what exactly the sun path diagram is. Okay, so sun path diagram is basically a 2D representation of a sun dome. So what is a sun dome? To measure the Earth's relative position of the Earth, to measure the sun's relative position from the Earth is why we use the sun path diagram, right? So you have a horizontal plane here, and say the sun is obviously in 3D space. So assume a dome that is covering this particular plane that you have chosen, and the sun moves from east to west, right? The sunrise happens at the horizon level. So it starts from east, makes its way across at a certain angle, and then sets in the west again at the horizon, right? So our horizontal plane is basically the Earth's horizon. And this, when you plot it on a 2D compass-like diagram, which is called the sun path diagram, is when you can determine the sun's relative position. So you can determine at what angle the observer is observing, or relative to north, at what degrees is the sun moving, right? Because the sun moves more towards the south during winters and is almost above our head during summers, right? In the southern hemisphere, it's the opposite. So let's take a look at all the different values and all the different lines on the sun path diagram. So this circle is basically this horizontal plane that we're plotting. And these lines the radial lines here are your azimuth lines. What is an azimuth? Every time you say the word azimuth, is basically the relative position on a horizontal plane. So if, let's say, the sun is at this angle here, right? And you have this circle, and this is north. This sun's position somewhere corresponds here, right? This is west, this is east. So the angle of this, from this point, measured from north, is called the azimuth angle. So the sun can be at any angle over here, and it's always relative to north. So at north, it's 0 degree azimuth, and before at west, it's 270 degrees. At east, it will be 90. And at south, it will be 180 degrees. So this relative position with respect to the horizontal plane or the horizon line is what your azimuth is. Okay. The next thing on the sun path diagram are these concentric circles. Moving out, these concentric circles, and they each have a value going from 0 degrees outside and 90 degrees at the center. Not sure if it's visible. Let me just redraw it in black. Right? It's 0 degrees. The outermost circle is 0 degrees, whereas the innermost circle is 90 degrees. Okay, so what this is the altitude angle. Like I said, you have an observer here and the sun is here. The angle the sun makes with this observer is called the altitude angle. Azimuth angle is usually represented with alpha. Altitude angle is usually gamma. Okay, so this angle is called the altitude angle. Now, if there is an angle of, at what angle do you think it will be 0 degrees? 0 degrees. If the altitude angle gamma is equal to 0, will the sun be at the horizon? Or will it be right above the head? the altitude angle, which is your relative position of the sun with respect to the horizon and their line of sight. This angle, gamma, if it's 90 degrees, okay, 1 second. Just give me a moment. I think I have some issues with the connectivity. I'll be right back. Yes, hello. Sorry for the disturbances. Was everything I said clear with respect to like network issues or anything like that?
Yes, ma'am. Clear.
All right. Yes. So yes, if it's 90 degrees, it means that the sun is right above our heads. And if it's 0 degrees, the sun is at the horizon. It's either in the east or the west. Okay. And the next lines that we see on the sun path diagram are these curved lines here. Okay. These lines represent the dates. Usually, because we cannot fit all 365 days into one path, they have months. They represent basically months. So the first line is always the June. First line in the sense, the one that is closest to the center, because we're in the northern hemisphere, is June. The one that's farthest is December. Right? All the other lines that are together will have 2 months coinciding with them. For example, this will be July, August, so on till December. And then again, afterwards, this line will be November, December, right? So after December, again, Jan, Feb, March, April, May till June will coincide. So there always be 2 months with every other line. So July and May will have coinciding sun path diagrams. November and Jan will have coinciding sun path diagrams and so on. I would suggest you go to Andrew Marsh, which is a website. Andrew Marsh. So he has a lot of MARSH, Marsh. So this is a website where you can actually go and select the sun path diagram for whatever latitude or whatever place you are in. And you can click each of the aspects or different parameters and check how it varies and how the sun moves. There's also an animation to see which line the sun follows, etc. I'm sure you would have used this before, but to those of you who don't know, you can also check out this. And there are many other software. So under Andrew Marsh, I think 2D sun path will give you this. It's a really interactive tool that can help you understand this better. Okay. So one question to you all is, say I'll give you 2 locations, right? At 23 degree north and 14 degree west and 23 degree north and 15 degrees east. Okay, the other set of locations are, say, 14 degree north and 14 degree west, or 27 degree north and 14 degrees west. So here we can see that the 23 degree latitudes are same, but the longitudes are varying. Here the longitudes are the same, but the latitudes are varying. which set A or set B, will have the same sun path? Do you think these two locations will have the same sun path, or will these two locations have the same sun path? Just to clarify, if this is your Earth, this is your equator, all these horizontal lines are your latitudes, and your vertical lines are your longitudes. So latitudes always represent in degree north or degree south, and longitudes are represented in degree east or degree west. So among these two sets, these locations which have coordinates of latitude and longitudes, in which in set A the latitudes are the same, and in set B the longitudes are the same, which set will have the same sun path diagram? Can anybody guess? Lavanya says A. That is, the sun path diagram for the same latitude will have the same sun path. Actually, sun path diagram varies with the latitude. So each latitude from the equator till the poles, each of the poles, North Pole and South Pole, each degree latitude will have its own sun path diagram, because the angle of the sun varies with the latitude. Longitude, not really, because the Earth revolves, right? Because day and night happens, it rotates on its axis. Each longitude will receive the same sun path. But latitude, because the Earth's shape and the axis of rotation, each latitude will have its own sun path diagram, which means each latitude has its own sun path. You can plot it for every latitude. So even in the questions that GATE asks, it specifies the latitude at which the sun path is for. Okay. So let's go back to the sun path diagram. There are more lines to look at. So we figured out the angles of the sun with respect to the azimuth. We got the altitude angles. We saw all the dates and the month lines. Next are these lines, which I don't know if you can see, but they're in dotted. Okay. These are the timelines. These represents time. They're obviously from sunrise on the east to sunset on the west. Okay. So the line right at the middle will be 12 noon. Because sun is right overhead us, the angle is 90 degrees. This center line timeline is always 12 noon, and more often than not 6 p.m. will be the sunset. So all of this here will be your sunset, and whatever line is coming here will be your 6 a.m. and that's your sunrise. So if I were to plot a say Feb 28 2 p.m. I would say that okay, February line is over here, right? This is the Feb line. And in this line, 2 p.m. will be 12, means 1, 2 here. So at this time, altitude angle is say 90, 80, 70, 60, 50 degree altitude. So my gamma is 50 degrees based on this concentric circle, right? And my azimuth angle is almost say 230, so 227. Here this is 230 and this is 220. I'm not sure if it's visible, but here the value which coincides here is around 227 degrees. This is how you calculate the altitude and the azimuth angles. If you have a sunpath diagram, they'll give you the date, they'll give you the time, and you'll have to plot the coinciding lines on there, and then you'll find the altitude and the azimuth angles. Okay. So now we know the sunpath diagram, we know where seasons happen. Then we know how to find the altitude and the latitude and the azimuth angles. What do we do with these angles? What are they used for? Any doubts till now? Tell me if you have any doubts, or I'll move on to the next slide. No doubts? Okay. Moving on. Moving on, let's see what exactly all these azimuth and altitude angles have to do with architecture and why, where and why we'll use them. Okay. So this is just a representation to first understand two things. One, you have a solar azimuth angle here. Right. This is a solar azimuth angle. They're saying from this angle till this angle here. But actually we're going to measure it from the north. So solar azimuth for us will be from wherever this point is, the sun is on this point, right? From this till here in the northern hemisphere will be our solar azimuth angle, right? But if we have a wall, say I have a west facing wall, okay? Then the wall also will have an azimuth angle. Azimuth angle is basically the angle it makes with the north direction. Okay, you can remember it that way. Angle between an element, usually it's usually used for the sun, but for architecture we use it with walls as well as any other vertical element that makes an angle on the horizon plane. Okay, so even the wall in this case has a azimuth angle. Okay, here they've taken with the southern hemisphere, so they have a surface azimuth or the wall azimuth with respect to south. But in the northern hemisphere, we take it with respect to north. Surface tilt, again here, if there is a plane and the wall is straight, then the surface tilt is 0 degrees. But if say the wall is inclined, then this is known as a surface tilt. Surface tilt is with respect to the perpendicular, not the horizontal plane, is with respect to the perpendicular. Okay. So with solar altitude and azimuth angles, right? This is your site. You always take it from a perspective and you drop a perpendicular from the sun. Then this angle is called your altitude angle. Altitude angle is gamma. Is your angle between the observer on a horizontal plane in line of sight. Okay. This is represented by gamma. Solar azimuth angle alpha is the perpendicular drawn from the sun and the north. All right. I just gave you the definitions so that in the future also, if you have any doubts with respect to these terms, it will be easier for you. Also, you can draw a graphic like this that will help you remember what azimuth and altitude angles are. Right? Shall I move on to the next slide?
Yes, ma'am.
Okay. So using the solar azimuth and altitude angles, we can design sun shading devices. Okay. So the first type of sun shading devices that we can see is a horizontal shading device. So if I say have a window that is W meters wide and H meters in height. Okay. A horizontal shading device is nothing but the chajja, which is a horizontal projection that I can propose. Now this length or the width of the chajja is determined by these sun angles that we previously saw. Right? So to calculate this, if I were to say draw a perpendicular this way, right? Then this angle, let me draw it in a different color, it will be easier for you. Okay, if I were to say draw these lines, no, incident angle of sun, and if I were to take this horizontal line, then this angle is called the vertical shading angle, the vertical shadow angle. We need to calculate vertical shadow angle to know what the width of our chajja should be. For example, if I take this triangle here that is formed, then I know that this is L, which is what we need to find. And this is your VSA, or your vertical shadow angle. And I know this from the height of the window, which is given. Okay. So can anybody guess how to find L?
Pythagoras
It's a
theorem.
VSA. Sorry?
Like Pythagoras theorem.
Pythagoras theorem will give you this.
Okay.
Right? I have an angle here. I have VSA angle. We use tan theta, trigonometry, right? So what is tan theta? It's the opposite by height, adjacent, right? Again, just to recap, we'll be using this in your other subjects as well. Tan theta is opposite by adjacent. Sin theta is opposite by the hypotenuse. Cos theta is adjacent by hypotenuse. Just make a note of this formula. You've learned all of this. We don't need the derivations. We don't need anything else. All these tiny formulae will be used for calculating many other values and quantities. So if you can't remember this from your high school, just make a separate list of it so you can always refer and remember it. Okay. So VSA, tan of VSA will give me the opposite, which is height. If I say tan VSA, will give me height by length. So obviously, to find my length, I can just transpose will be the height of the window divided by tan of the vertical shadow angle. Okay, we'll come back to this. We'll see how to calculate the vertical shadow angle. Similarly, if we have to calculate a vertical shading device, what is a vertical shading device? I have a window again. That is W in width and H in height. Okay. My vertical shading device will be like the fin. That blocks light from the opposite side on the vertical sides. Okay. So to calculate this, similar to the previous one, if I were to draw an angle this way, right? That will be my horizontal shading angle, horizontal shadow angle. Okay. So to calculate how much depth or width I need for this, I need to calculate horizontal shadow angle. And for a horizontal shading device of depth L, I need to calculate the vertical shadow angle. Let's see how to calculate these things with the example of a question. Okay. I'll just write the question down. I don't have the printed question. Give me a minute. I'll just go back to the previous slide in case you need to copy. Right. Okay, a minor correction here. I have a window here and I have my vertical fin. When I'm calculating, I need to calculate the horizontal shadow angle, right? So the angle is made with respect to this fin. So this angle is my HSA. Not the other one, because obviously we need to find out the width of this. So this angle made between the width, between the angle of that vertical angle and the angle of incidence from the solar sun rays will be your horizontal shadow angle. Okay. So write down the question. A window of size 1.5 meter by 1.5 meter is provided on a south facing wall. Okay. We need to design a vertical shading device and a horizontal shading device. Okay. From sun path diagram. Usually in GATE, they don't ask you to use a sun path diagram, but if you're really unlucky, maybe you'll get one next year, but we know how to find out the angles from the sun path diagram. gamma, which is our altitude angle, is 40 degrees. Alpha is 140 degrees. Okay, so this is the question. They've given us a window of size so and so on the south facing wall. We have to design both a vertical and a horizontal shading device. They've given us the altitude angle and the azimuth angle. Okay. So let's draw the window again roughly. This is my window, 1.5 by 1.5. Okay. So let's first look at how to calculate the vertical shading device. For the vertical shading device, we need to calculate the HSA, which is the horizontal shadow angle. Horizontal shadow angle is given by delta, and the formula is the absolute value of azimuth angle of the sun minus the azimuth angle of the wall. Okay. So this mod brackets, that just means that whatever value you get by doing this operation, the positive value is what is considered. Okay. So if I have a negative value, it's considered just to be the positive value. So here delta says azimuth angle of the sun minus azimuth angle of the wall. Now the solar azimuth or the azimuth angle of the sun is already given. So we know that alpha sun is 140 degrees, right? Now the azimuth angle of the wall is calculated with respect to the facing of the wall to the north, right? So we know here that it's a south facing wall. So if I'm going to draw a compass here, this is north and the wall that we are considering is facing south. Then the angle it makes with north is, any guesses?
135.
Sorry, my voice is breaking. Is it still breaking for everyone or is it?
It's okay now.
Okay. Okay, so, sorry, somebody said 135.
Yes, ma'am.
Okay. No, actually, say I have a south facing wall. What is the angle south makes with respect to north? So we know that east is 90 degrees. Then again, you add another 90, it will be 180 degrees. Then another 90 will be 270. And north will be 360 or 0 degrees. So the angle the south face makes with north is 180 degrees. Similarly, an east facing wall will make an angle of 90 degrees and a west facing wall will make an angle of 270 degrees from north. It's always measured clockwise. Is this clear? Why it's 180 degrees? Hello, am I audible?
Yes, ma'am.
Okay, it's clear, right? Why it's 180 degrees?
Yes, ma'am.
Okay. So now we have the vertical shading device or the vertical fill that we have to calculate. Let's say the depth of it is L, right? We're actually calculating this angle delta. Now we know that delta here is the wall azimuth minus solar azimuth. So delta is 140 mod of 140 minus 180. Because it's in mod, it's in a modulus here. It's the absolute value, which means it's a positive value. So it's 40 degrees. Okay. So now we know that delta is 40 degrees. If we take this triangle again, this is 40 degrees. This we know from the question is 1.5 meters. We need to find out L. So L will be 1.5 divided by tan 40, like we discussed previously. Can anybody find out and tell me what the answer for L is? .5 by tan 40. You know how we got this, right? It's opposite by adjacent, which is 1.5 L by 1.5. 1.5 by L is tan 40, and then you just transpose. Anybody got the answer?
Is it 1.34?
L is 1.34?
Hmm.
Okay, let me just cross check. Is everybody getting the same answer?
1.787.
Let's just check. So it's 1.5 by tan 40. I'm getting as 0.839. Which is I'm getting 1.787 meters. Cross check whoever got 1.34 because L should be 1.5, which is your width of the window divided by tan of 40 degrees. Tan 40 is 0.839. So 1.5 divided by 0.839 is 1.787 meters. Okay. Like I said earlier, while calculating, always calculate till the third or the fourth decimal place. And make sure you don't have tan for negative values. It's always from 1 to 0. So tan 40 is the right way to do it. Okay. Any doubts?
No, ma'am.
Okay. So now let's see how to calculate the horizontal shadow angle.